let's come back and to add a few more about diagnostics. So another thing that in that we can measure electron number density, electron temperature, electric field, and now, and a most important thing is to measure that the non-equilibrium with is the vibrational states and the species and in the plasma. So, and in combustion field that the CEFRC method has been developed, particularly recently you have picosecond laser that can, a broadband, they can ultra fast and excited in many vibrational states at one time so that it can allow you to detect the vibrational states and which you typically has to change that the laser one by one. So for example, that allow that if you see here that the CEFRC is a 4-wave or 3-wave process that involving a pumping laser to pump the excited state, and you have a Stokes beam that trigger that the energy transfer and to the ground state, and you have a probe beam to excite the molecules at the excited states, and then you probe that signal of anti-Stokes signals. And this is that allow you, the signal is because it's coherent and it is much stronger than the Raman process. But they can allow you to do a one-dimensional measurement and in the process. So you basically have 2 laser beams and 1 probe beams, and then you generate a signal. So as a lot of diagnostic has been developed, the good point for a femtosecond laser is femtosecond laser that they have broadband. So if you're using this broadband laser, you can pump in that the molecular to a steady state. And then if you're using a Stokes laser, you can measure the signal from that excited state to the lower state. And then, and at the same time, that the same laser beam can also excite another vibrational state with the same wavelengths. So therefore, that you can detect that the signal of many vibrational states at the same time, and by using this CEFRC measurement. I try to show you. Well, it's not moving. I'll try to show you that the computer is okay. So it's working now. What is that the current strategy to do this CEFRC measurement? So this one is early state, and at Ohio State, they did this using picosecond laser to measure that the plasma discharge between 2 sphere to sphere. And what they did, that they try to, this is that the temperature as a function of time, and then they measure that the result, they measure that the temperature, atomic oxygen measurement is in Talif, and you measure the vibrational nitrogen temperature and using the rotational temperature. So this CEFRC measurement allows them to measure non-equilibrium temperature distribution and in the plasma as a function of time. And you're adding a Talif measurement, and you can measure atomic oxygen. That correctly and understanding the mechanism about that the nitrogen vibrational excitation and a vibrational energy relaxation, and then that the energy transfer process. So this also gives you that the opportunity to understand that how that all the number density and the pressure and temperature change. So this are our early measurement about this all kind of species using CEFRC measurement and Talif measurement together. So, and recently that in 2017, a group by Joe Michael, who graduated from Princeton, was a professor at, I don't know which university, and published a paper using 4 beams. They have a pump beam excited vibrational state, and you have another pump beam targeting on the rotational state, and you have a probe beam to generate this a car signal. So this kind of 4-beam diagnostics, it can simultaneously detect that the vibrational state and the rotational state. So allow them to measure this plasma. They can measure vibrational temperature and that the rotational temperature, and to detect that the difference, and at the geometry, you can see that the age effect is still have very strong vibration at the age. So this diagnostic basically is capable to detect that temperature, but you require 3 lasers. One is that a vibrational laser, the other one is rotational laser, and the third one is that the picosecond laser. So you need a lot of investment to do this job. And the question to me is that I only have 1 femtosecond laser in the lab. How can we using 1 laser and to detect both vibration and that the rotation? So here that if we're looking at the energy shift depending on vibration rotation level, and that this the distance between the 2 vibrational molecules, they are highly dependent on the vibrational levels. If you have a vibration level that is increasing and that dV is increasing, so you're making that the energy gap and the energy smaller, so you're causing that the vibrational energy redshift. So if you're using 1 laser, femtosecond laser, and you do a rotational course, this is the rotational course at a different rotational level, and you can see this the wing that of that the rotational level is broadened by that vibrational state. This is caused by this redshift of a high level vibration. So therefore, they can be, but you're fitting that this redshift, you can fit that vibration temperature, because in vibration temperature you don't need to be accurate a few degrees. You only need, they are the thousands of temperature. You have hundreds of degrees, fine. So you can measure this vibration temperature and very convenient by using just 1 femtosecond laser. So here is the experimental setup, and initially was set up at Sandia, and they're using this 2 pin-to-pin electrode, and then this housed in a chamber, using this is the probe laser, this is the pumping laser, and then they create a car signal, and you can measure it. So here is that what we measure, that the vibrational state temperature is about, is about 2,000 to 5,000 degrees. And this rotational temperature is between room temperature and about 375. And yet, also the distance from the cathode, you can see the vibrational temperature is very different, varying and along the distance from the cathode to the volume. So therefore, and quantitative measurement and using this rotational course can allow you to measure rotational temperature in a one-dimensional distribution, so that you understand how that the plasma discharge is affected by near the cathode and far away from the cathode. So, and then the other thing that is that how can we measure that the non-equilibrium using this kind of coarse coherent beating? That, for example, if you have a probe laser that is a 65 picosecond, then you need to buy a separate picosecond laser, right? What if I only have a femtosecond laser? I can using optics to delay and to generate that laser to make a 6 picosecond laser. If you want to use 6 picosecond laser, there's some broadening because the laser beam is very pulse is short. So therefore, the spectra is broadened. If you're using the broadened picosecond laser to do the course, you can see a lot of signal is beating. So people just, okay, throw away this. This is terrible. We just don't use it. But the question is that how can you using this kind of a coherent beating between this probe laser of picosecond laser with the femtosecond laser, and you can fitting that the curve of the beating to extract that the vibrational temperature. So here that the Tim Chen, a graduate student, did this work, and basically saying that by using this modeling, this beating, you can measure that the rotational temperature and vibrational temperature at the same time. So this will dramatically simplify the diagnostics. You're just using one femtosecond laser. You don't even need to buy a picosecond laser, and so that you can using this beating to extract that the vibration and rotational temperature. So it's dramatically simplify the system. So the next thing that is TALIF. TALIF is very useful and for measure atomic species like oxygen to see how oxygen atoms is going to affect the combustion, and to see how N atoms to affect that ammonia synthesis. So measuring that the atoms of TALIF, you're basically using 2 photons and to excite virtually electronically excited states, and then they give you a fluorescence, and you can collect the fluorescence and you compare to calibrate with a known atoms. So they can find that for example, the TALIF is a 2-photon process, is basically proportional to the square of the laser. And so here's a measurement for example, a N atom for the ammonia synthesis. We try to pump that to the ground state with 2 photons to get into the N atom excited state. We collect the fluorescence at this transition between this. We compare with a krypton, TALIF, and they are almost similar energy gap as a similar wavelengths. So you can detect this N atom by normalizing that the signal between a TALIF of N atom and krypton, and then you obtain a number density. So here that the tricks. You have to be conform the TALIF is actually proportional to the square of the laser pulse. So make sure that your measurement is good. Second, you have to be careful using krypton to make sure that the signal is linearly proportional to the concentration. So 2 things you have to be verified. Once you verify this, you can see we can create a nitrogen-hydrogen plasma, and then using this TALIF to measure that the number density of N atoms. This is a model prediction. This is that the experimental measurement at a different frequency. So this is really helpful and for quantitatively measure some of the atomic species and in the plasma discharge. And another thing that you try to measure OH. OH is one of the most important things in plasma-assisted combustion because at low temperature they form a lot of O, and O will become OH. But the concentration is very low. So how do you really to measure the OH very sensitively? Typically, people are using laser absorption spectroscopy to do so, but laser absorption spectroscopy really cannot really get you to the number density you want. But this kind of a femtosecond laser, a cavity enhanced absorption spectroscopy, that can help you to do a UV and OH measurement. It gets you down to the level of ppb level of sensitivity. So therefore, this allows you to do a single shot femtosecond laser and a cavity enhanced absorption spectroscopy to do a very sensitive diagnostics of OH radicals. So I think that try to convince you that this kind of femtosecond laser that they have the advantage compared to the infrared laser. The infrared laser, they have sometimes that the signal is weak, and UV absorption sometimes is very strong. And you can take the advantage using femtosecond laser to do this laser absorption spectroscopy and to do that. And also that the femtosecond laser, because it's broadband, they can multiple lines will absorb. And you can use in the multiple line to fit your spectra to make it more accurate than just a single line of measurements. So this is that a example about that the laser diagnostic in terms of by Crystal Locks, as I presented before, that they using this kind of measurement of cavity ring down spectroscopy, and using combined with a TALIF, and so they can measure all this ABC state with atomic oxygen. They give you very accurate time-dependent measurement about atomic oxygen, and then how that they into B and into C as a function of time. So this quantitative diagnostics is really give you a wonderful tool to understand the kinetics in plasma. So this was really the wonderful the early days. The electrons and collided with nitrogen to form this ABC excited, and the ABC decided to dissociate oxygen into 2 O atom, that 2 O atom, and do a lot of combustion enhancement, which is combustion people we understood. But the diagnostic really is the key to understand what is the mechanism in terms of plasma, right? So that I don't want to repeat anymore. So there's a lot of TALIF measurement, again, atomic oxygen in air. And once you have ethylene, it's a room temperature, remember, that the O atom formation is much lower, because that the O formed in the plasma is going to react with ethylene that get consumed. So this kind of quantitative diagnostics really give you a lot of measurement. And this experiment I showed you before is about a singlet oxygen measurement, and give us also a quantitative measurement about what can be done, and to using laser absorption to measure a molecularly electronic excited species. So I don't want to repeat again. So the next thing I'll try to show you is that is a Faraday rotational spectroscopy. So in combustion, one of the very important species is that HO2. HO2 radicals is so important, but no one in combustion really can quantitatively measure it. It's a two approach in Stanford, Ron Hansen, and then in Lund University, the Marcus Ardeen. They basically, okay, we're using UV light to break down this HO2 to form OH. Then we measure OH. But once you do that, and you break down this, and then the chemistry becomes very complicated. And there's so the way to do this that we're using, because these two, they are paramagnetic molecules. So this is absorption, typically, and without a magnetic field. If you put a magnetic field, and the electron orbital will be aligned to follow that magnetic field. So when you force the electron orbital to change the direction, and this rotational quantum number, they will split. They split into the J equal to 3 divided by 2. You multiply by 2 plus 1. That means it will split into 2J plus 1 will be 4 states. This depends on electron spin directions. So you put a laser that is linearly polarized in a left-hand side rotation and right-hand side rotation. So this absorption about this HO2 will be dependent on that the electron spin directions. And so their absorption will be different. And therefore that a left-hand side light will be more absorbed than the right-hand side, that the light. So the polarization angle will change. By detecting that the polarization angle change, you can know how much HO2 you do this. So therefore, this method is not going to be affected by the water, by OH radical, by something else. That allow you to do a direct measurement of HO2 radicals. This allow me to do this diagnostics I showed you before in terms of HO2 measurement and using a magnetic field coil and laser absorption spectroscopy, quantitatively measure, generate a singular D from a photolysis of ozone, and then all these reactions can be detected by OH and HO2 using this. So, so this is the HO2 measurement. This is a feeding of the reaction rate. We just talked to you in a few minutes before. So, and then molecular beam diagnostics is another way that people in Niels Hansen at Sandia, they're probing all these molecules by using molecular beam. So they can detect many, many species and peroxide species and ketones and alcohols and the acid and in the species. So all in all, what I try to say is that this kind of laser diagnostics, molecular beam for rotation, that give a lot of advantage about people in combustion field. They can do typically something plasma field they normally don't do. So that is why that you need to borrow the tools from other fields and to tackle the problem of another field. That's really helpful. And in my lab, we developed this a hard cell measurement. We have a DBD, and we have a lot of tunable lasers in the laboratory. We can do time-dependent measurement of the multiple species diagnostics. We can compare that to the computational modeling and developing models for combustion. And I don't need to talk to you too more. We developed the mechanisms for endodecaine and all the hydrocarbons with plasma-assisted combustion. And this is the experimental data. This is the computational modeling. So by doing this, you can develop a lot of plasma-assisted combustion models, experimental validated, so that can do a combustion synthesis modeling and this chemical synthesis. So I don't know how much time I left, but I need to finish something so that I have time for tomorrow. I have about 30 minutes, correct? So probably I want to fly through, don't want to spend a lot of time in terms of validation. So what I try to conclude is that the modern diagnostics and give you a lot of advantage to detect the time resolved species and even spatially resolved species distribution. And that allow us to model plasma properties and also that the plasma-assisted combustion process. And that help us develop models that we normally don't know in plasma-assisted combustion. So the next thing I want to finish today is that is instability. And because plasma is always become unstable, and people need to understand that what is the instability and how that be modeled and controlled. So we talked about the plasma-assisted combustion, and then we'll talk about the plasma chemistry, and you talk about plasma diagnostics. And now we try to show you what is a plasma instability. So here you can see that the something I briefly mentioned yesterday was that you put the fuel into the air, and you start to see the instability start to develop. And then this was that I tell my people that this was 2019, May 27. I was flying to Beijing to attend a conference, and I was reading the newspaper, and they published this. You can see that the lightning struck the head of the rocket. This is the Russian rocket. And then this is the tail gas, and the lightning just goes through this tail gas. That triggered me is to understand why that everybody know the rocket exhaust gas, they are what? They are unburned hydrocarbons. So then I Googled that the CE and the science paper. There was a Nika Augusta. They say, okay, lightning struck that the forest fire, and the forest fire, because when they burn, they create a lot of hydrocarbons, and that hydrocarbons is catch lightning. So it seems like here. So then that really triggered me to try to understand that in a lot of people doing ammonia synthesis, and the plasma in ammonia, it seems to be very stable. And that's the opposite to unstable in oxide. And what is happening, and people try to develop advanced engines, they want to understand the plasma instability and how to control it. So anyway, so what is the mechanism of plasma instability in a reactive mixture? All right. So the old days that plasma physicists, they build this kind of a vacuum tube. They have an anode. They have some kind of mercury or something. They discharge your plasma. The plasma becomes very volumetric. But at a certain condition, the plasma suddenly contract into a very skinny arc. And then they try to understand what is that the contraction is just like instability. So sometimes they say, okay, and you have a plasma, and then in the head, you got a lot of, glow discharge, and in the bottom part, the plasma contract become a leader or contraction. So try to understand this. This is that if you have a current, and if the current is really small, like this, current is very small, and then you can see the electric field is very high, yes, and then you generate a uniform discharge. When the current over critical data, and then that suddenly that the plasma collapse and form this kind of contracted things, and this and if you reduce that the current, and then you go back to the uniform discharge. So this is, I looked at this diagram. This is like similar to combustion. You see that this seems to be auto-ignition and the flames and the extinction and come back to auto-ignition. Or you like a cool flame, hot flame. Cool flame become hot flame come back, become cool flame. It's the same thing. And the question is that what is the mechanism? So the mechanism is that if you have in this kind of a plasma, if you have electron number density, and if you increase the current, that means you increase the heating. When you increase the heating, that the temperature is rising. If the temperature is rising, that the number density is decreasing by ideal gas law. When the number density is decreasing, and then that E or N is increasing, that means the electron temperature is gaining. If the electron temperature is gaining, they collide with the neutral molecule to give you more electrons. And this process they keep doing, they call a thermal instability. And in plasma people, they're talking about instability. One of them is thermal instability. And so this thermal instability was studied a lot in terms of argon, nitrogen, and no one really want to look at that instability when you have hydrocarbons. So what if you have hydrocarbons? Well, you're looking at this, you have a hydrocarbon mixture, and I know that everybody in this room right now, hydrocarbon, you have high temperature, intermediate temperature chemistry, low temperature chemistry, and plasma, we're coupling with this a lot of reactions. The question is that how does this is going to affect my instability? So it's just out of curiosity. And then when I come back from my trip, I submitted a proposal to National Science Foundation. I said, I want to study something new, instability. So this is what we understand. And this is what we don't understand. And this is my hypothesis. My hypothesis basically says, if you have fuel, that electrons impact the fuel, they paralyze the fuel, and they create a vibrational energy excitation, and they create electron attachment to water. They create that heat release, that increase that your mean free path. They create that the composition change, they change your plasma chemistry. And some of them, they increase electron density. Some of them, they decrease electron density. They will be different from that thermal instability. And then the proposal was reviewed, and then they got funded. So now I got time to work on this. This is how that people, you want to develop a proposal. You have to have an idea, and you have to have a question, and then hypothesis, and you propose it. And likely you will get it funded. And I was saying that we have a dean of research at Princeton 2 years ago. Suddenly they say, nobody should collaborate with fossil fuel companies because fossil fuel companies are bad. And I had probably $1 million a contract with ExxonMobil. All of them are gone. But the committee make an exception. Say BP is good. Why? I look at what BP oil is different from ExxonMobil oil? No. His answer is the BP funded this climate change people. And that's why they make it BP is good. I'm very annoyed with this Princeton University, that the dean decision. And I said, you need to compensate me because I lost the money. And I said, he said, no compensation. This is a university decision. Okay. I said, you have to write me in an email. You do not compensate. I need $400,000. You have to give it to me. And the next day he called me, okay, let me have a talk. And they give me a check, $400. And later, and he resigned. And it's really bad. And I feel that it's too bad. I don't want to work with this thing. And then they created a new energy innovation, energy innovation grant, $300,000, only one every year. So in the first year, I feel I didn't want to write anything. This year, I thought maybe it's an opportunity for me to write something. I write a proposal. I thought that likely will be funded. And then I submitted probably in March. In May, I got a letter. Professor Ju, congratulations. You're funded by this one. It was announced yesterday on the Princeton website. I was the only one announced by this. So what I'm trying to share with you that don't worry about funding. The only thing worry about whether you have great ideas, right? Once you have great ideas, you always can find money, right? Money is the nexus. You believe America is a great country in the world is because that you have a great idea, likely if you don't win here, you probably will win somewhere else. You bet this country has appreciate your ideas. So it's just like a gossip. Okay. So this is that the student want to do e-fish, and then they want to try to put some kind of a measurement, and then we put a methane into oxygen into argon. You can see there's a pulse number 25 and a pulse 100. You start to see the instability start to develop experimentally, and this is that Eric Russo. Right now, he's a program manager, and in Lawrence Livermore, charge multi-million-dollar per year now, and. So this is very exciting when I see this happening in the lab. And so you can see this is air, and you are uniform, and this is that with methane, you are getting instability. So that means that the instability is strongly changed by the combustion chemistry. So if you measure that electric field I talked to you before, this is that the validation. When you can see that applied electric field, electrical measurement, you validate that your measurement is good. So now that you can see there's a discharge. Once you have discharge, this is the before breakdown, after breakdown, electric field quickly fall, and everything here, there's no electrical field because of the Debye shielding effect. But this shielding will change when you add more oxygen into it because the electron number density becomes lower. You start to see the weakening of shielding. You start to see some electrical field. See, understand? So this is very interesting in physics. And you try to measure that the